Hello, everyone, and let me welcome you to this NISS webinar series. We're going to continue to hold for a few minutes. I have 11:59 right now. We'll wait just a minute or two because I see the numbers still increasing in our participants, but we'll go at maybe a minute after. Just wanted to welcome everybody. We're still waiting. We're going to go at a minute after. I have 12:01. I'm in Eastern Standard Time, and it's 12:01, so we're ready to get started. Thank you, everyone, for joining our AI Statistics and Data Science in Practice webinar series. This is our third event in this series, and this is sponsored by NISS, the National Institute of Statistical Sciences. Previous events, which were held in October and November, are available on the NISS YouTube channel if you'd like to go back and see those. And our speakers, this webinar will also be there, should be there a week or two after this event is held, if you want to go back and review it again. So I'd like to welcome our speakers. Dr. Victor Lowe is currently Senior Vice President of Data Science and Artificial Intelligence at Workplace Solutions at Fidelity Investments. Previously, he managed advanced analytics teams in personal investing, corporate treasury, managerial finance, and healthcare and total well-being at Fidelity. Prior to Fidelity, he was a VP and manager of modeling and analysis at Fleet Boston Financial, which is now part of Bank of America, and a senior associate at Mercer Management Consulting, now Oliver Wyman. Victor's also been a visiting research fellow and corporate executive in residence at Bentley University. In addition to Victor's professional services to NISS, he's on our affiliates committee and also on our planning committee for this session. And he's done many other service roles for NISS, so thank you very much, Dr. Lowe. He's also been serving on the steering committee of the Boston chapter of Informs and on editorial board for two academic journals. Victor has a master's degree in operations research from Lancaster University and a PhD in statistics from the University of Hong Kong, and was a postdoctoral fellow in management sciences at the University of British Columbia. He's a co-editor of a graduate level econometrics book, published numerous articles in data mining, marketing, statistics, and management science literature, and is finishing a graduate level textbook on causal inference for business. So you're going to see the benefits of that today, because today he's going to be talking to us about causal inference techniques, which have had application across many of his areas of interest, including customer relationship management, marketing research, advertising strategy, risk management, financial econometrics, and insurance. So we're happy to welcome Victor with us today. Let me also introduce Dr. Victor Chen, who recently moved to Amazon People Experiencing Technology Central Science to take a position as head of Science Excellence. There, he's leading a team on an interdisciplinary group to improve research into decisions and products, centralize institutional knowledge, and build an ecosystem of science-related tools. Before Amazon, Dr. Chen was the Director VP of Data Analytics and Insights, Experimental Design, and Causal Inference, our topic for today, at Fidelity Investments. At Fidelity, he led the development and deployment of the first enterprise-wide platform on causal and experimental analytics. So big accomplishments. Dr. Chen has also been a fellow and emerging market global players global coordinator at Columbia Center on Sustainable Investments, an economic officer at Asia Pacific Gateway and Initiative Corridor Coordination, and that's for the Government of Canada, and a research fellow at Asia Pacific Foundation in Canada. He's built 2 startups. The first was TNC Online, a digital service company focusing on synthesizing economic analysis into analytic tools to identify the sources of foreign direct investments into Canada. And a second, during his academic career, Go Peaks, which was a startup devoted to research and technology development to accelerate and scale knowledge synthesis from social, economic, business science into real-world decision solutions. It's especially focused on knowledge graph-based prescriptive, causal, i.e., analytics. Dr. Chen holds a degree in economics from the University of Ottawa, a master's in information and data science from the University of California, Berkeley, and a PhD in strategy business economics from Beatty School of Business at Simon Fraser University. Dr. Chen was recently listed in the Business North Carolina Power List 2024 and named a CDO Magazine finalist for 2024 Top 40 Under 40 Data Leaders, among other recognitions. So today we're going to hear from Dr. Chen and Dr. Lowe about causal inference. That's been a focal topic of Dr. Chen's work for many years, and also very important to Dr. Lowe. So let me turn it over to you, Dr. Lowe, to share your presentation first.
Thank you so much for the introductions, Nancy. So I'm sharing my screen. Welcome, everyone. I would start by saying that I've been very fortunate to get into the joy of causality or causal inference or causal AI in the last several decades. As a learner, ongoing learner, and also as a researcher and business practitioner. And it's been really, really fun getting into this because I found that you will hear that. So with causality, there are lots of things that we can actually do, at least in the business world and in many other worlds as well. So here's the table of contents. And first, I will talk about why we care about causality. And I will introduce 3 major schools of thought. Each of these is very big. In this talk, we will focus on business applications, and we'll touch on some of these techniques a little bit here and there. There are many other seminars from NISS and elsewhere that will go into the very deep analytics ideas underlying each school. So we'll mostly focus at a high level, but we'll talk more about business usage. And I'll also talk about a specific technique known as uplift modeling, which is related. So let me just get into that now. So first, I would like to mention that there are multiple awards related to causality in the last 10 years or so. And the first one was a Turing Award for Judea Pearl. And that was awarded to him for his contribution to probabilistic and causal reasoning. And I will talk about that in a moment. And second, more recently, in Nobel Economics was given to 3 professors who used randomized experiments. Now, randomized experiments or randomized control trial RCT has been around for a very long time, more than 100 years. But these 3 researchers were able to use RCT to really solve many poverty and health issues. And so RCT could be extremely helpful in that way. In 2021, another 3 researchers actually were awarded a Nobel in economics on causal inference techniques using observational data. So I will actually talk about many of these in my presentation. Now, I just have a question here. Is there anything that that causal inference can support decision making? Okay. If there's no answer, I'm gonna answer it right away. Okay. All right, I'm gonna answer it in a few slides. So first, let's talk about correlation versus causality. Many of you are well aware of it. Uh, the time on your watch is highly correlated with the time on my watch. In the past, I like to set my time to be 10 minutes ahead, just to be self-deceptive. So not anymore, but at least in the past I did that. So if you plot a graph of my time versus your time, uh, it should be like this, exactly 100% correlated. Does it mean your time drives my time causally? Well, we all know that. This is a very simple example. Your time and my time are very associated. But if you change your time by a minute, it won't have any impact on my time because your watch and my watch have no causal relationship. What is really impacting your time and my time is actually something called the official time. There's some official time that is driving both the time on your watch and the time on my watch. So conditional on the official time, your time and my time are actually independent. So there's actually a conditional independency here. And as a result, this direct link between these two times should be removed, should not exist. Okay, so why we care about causality? So I'm going to dive into it now. There are multiple reasons why we care about causality. Whether it's in the business world, social sciences, medical world, and so on. So in the business world, we often do a lot of interventions. In the medical world, of course, we have medical treatments, procedures, and so on, right? And in social sciences and so on, we can change the health policy, we can change the economic policy. So people want to understand the impact of a policy change or a marketing intervention. We almost have the right to understand it, whether something is actually working or not. So impact of an intervention. A similar related thing is counterfactual questions. So what if the policy is different? What if this person didn't take the medicine? What would have happened? So all these are related to finding the effects of causes, or known as EOC. That's just basically answering questions which people want to know about that. And another one is explanation. So something happened. People want to find out why those things happen. Is it because of certain things? So this one is generally harder because you start with the outcome first, and then you want to trace what would be the possible causes, and you want to understand the causal mechanism or the pathway to get to the outcome. So this involves not just effects of causes, but also causes of effects. So given an effect, you want to identify the causes. So basically explaining why something happened. So in business, we want to care about, okay, after we know about attribution and explanation, so what are we going to do to make a difference? So how can we make the future better? So that's related to optimization. So that's generally under these three areas that's why we want to learn about causal effect or causality. So here are some examples in the business world. And I'm going to borrow the 4 P's of marketing. First P is price. So let's say if in marketing, if you want to change price, let's say you lower the price, this should generate a high demand, right? But you want to understand whether the demand, the demand would be high enough to justify the lower price. Another one is promotion. Another P is promotion. Promotion is just, what are the impact of direct marketing and advertising and other kinds of promotional efforts. And this is a causal inference question. And if we know about that, then we can optimally allocate the marketing dollars across different channels or different ways of advertising. Third, the third place is just the third piece is just place. So what if we change the location, or we open a new store, or make the store look different? What's the impact on the business outcomes? And that's a very important question too, because changing the location or opening a new store is a very costly event. We want to understand the business impact or predict the business impact. And last but not least is product. If we change the product features or create a new product, is it really valuable to your customers? So these are the 4 P's of marketing, and all of these are highly related to causality. Okay. So before we jump into causal inference or causal AI, I just wanted to talk about the most foundational thing is RCT, randomized control trial, that many of you are familiar with. Nevertheless, I wanted to just briefly mention it. The gold standard of measuring causality is through A/B test or RCT. And what it is really, according to Wiki, it has 2 things, 2 variants, A and B, and we wanted to compare between them. So let's say you are promoting a pair of shoes, some kind of shoe design, and you wanted to see whether which message would work better in terms of attracting your customers. So one way, maybe you want to focus on durability. Another way, you may want to focus on other things, special features, and so on. And then you randomly split your target group into treatment and control groups, and they are actually the same kinds of people, but one would receive one message, the other would receive another message. And at the end of the day, you wanted to see which message would give you a higher response rate. Response rates could be purchasing the shoes or clicking the website and so on. The beautiful thing about RCT is it ensures the characteristics, the features of the treatment and control groups are actually identical before the design, because it's randomly split. The treatment and control groups are basically twins, but one would receive one thing, the other would receive another thing or nothing. So it guarantees that the design is balanced in both observable and unobservable characteristics. So that's why it's so powerful. And it works, but in many cases, RCT is not feasible. So we need to rely on other kinds of schools of thought. So here's what I will be talking about at a very high level. Again, each of these is very big. Statistics, AI, and econometrics. They might look like they're competing with each other, but they're not. They actually share a lot of similarities, and they mostly complement each other. So I'm going to dive into the first one. I know a lot of the audience in this group are from the statistics field. So I'm going to get into the statistics first, also known as the Rubin Causal Model, RCM. And largely is related to propensity score matching, something that I will talk about in a moment. And these are a bunch of books. I'm sure there are much more you can find on Amazon related to the Rubin Causal Model or propensity score matching. It's not just proposed by statisticians, but also highly followed by social scientists and medical scientists. And it's been widely used, highly successful. Personally, I think it's because of the simplicity of it. It's pretty easy to apply and easy to understand. So inside the Rubin causal model, there's something called a potential outcomes approach or counterfactual approach. And what is potential outcomes approach? So let's say you're running a business and you wanted to retain your best customers. You don't know whether your retention program, the retention program could be just a phone call or could be a personal visit to hope that they would remain as your customer. So let's say there are 4 customers, A, B, C, and D. And if you don't call them, let's say just a call, they don't respond, that will be 0. 0, 1, these are the responses. If you call them y as the function of treatment, then they would respond 1, and so on and so forth. So sometimes you call them, they will respond. Sometimes you call them or not, they won't respond, like in customer B. Okay. Potentially. So that's what it is. But in reality, each person is only assigned to treatment or control, whether you call them or not. As a result, there are lots of questions here, question marks here. If they are assigned to control group, the control group A and B, you only have YC, you don't have YT. So those are questions. And how do you infer those missing data using this data set? This is called a fundamental problem of causal inference, because you can only observe one of them, not both of them, in most cases. So one way to do it is through some kind of statistical adjustment, such as matching or weighting. So in the business world, we love to do RCT2 or A/B test, they call it, but sometimes we cannot do that. So how do we do that? Well, if we don't have the RCT test, let's say you want to assess whether it's a sales effort. Sales effort could be a sales interaction with your customer. Whether the sales effort is working or not. So whether there's a direct impact on the outcome. Outcome could be buying a product. However, if you look at historical data, sales reps tend to cherry pick by demographics. They may pick those who have higher income or living in certain geography and so on. So those are called confounders. And we know that those features are causing not only the sales effort, but also driving the outcome. So how do we do that? Of course, we need to find a way to get rid of the confounders, if known. And one way to do it is to break the link between the confounders and the treatment assignment mechanism. And this that would make it clean. And then this arrow would come out automatically. This is exactly the idea behind PSM, or propensity score matching, or sometimes propensity score weighting. There are many variants of this method. So as an illustration, this is in a very simple case. How do we neutralize the bias or confounders? Let's say we have a basket of fruit, basket A, and we have another basket B. To make A and B to make B look like A, how do we do that? Well, A has 5 apples, B has 3 apples. So one way to do it is multiply number of apples, multiply the apples by 5/3. That would make it look like A. And likewise, you can duplicate the bananas and so on. So you can do that. So if you do that, then this basket C, after weighting, it looks like basket A. So this is essentially the weighting method behind propensity score matching. And this is just one dimensional, because we only have type of fruit as the variable. PSM handles multi-dimensional variables, many variables, and once you fit a propensity score model, you can use it in many different ways. So I won't get into the details of PSM, just wanted to give you some sense what the statistical approach works. And there are many courses and YouTube videos available on this, and it's a widely used method. The second method, which is less known, at least in the statistics community, is the Pearl Causal model, PCM. And it is basically from AI or computer science. And again, there are many books just like these, and there are more. And is created by Judea Pearl at UCLA. It's followed by a subset of computer scientists, data scientists, philosophers, and epidemiologists. And I make the word italic on subsets because not many computer scientists are aware of it. Because in statistics, let's say a good portion of graduate programs touch on causal inference, but not all of them. I don't know how many, let's say 50-50, or maybe even less. But in computer science, it's far less than that. But still, there are some computer scientists who have been spending their whole life, such as Pearl, working on causal inference or causal AI. So how is it different from the Rubin causal approach? The Rubin causal approach is basically a statistical adjustment. Now, the Pearl one is a little different. It's relying on something called DAG, or directed acyclic graphs. So in a graph, it's founded on graph theory. We have variables and links, or vertices and edges, or nodes and edges. And each variable is represented as a node. And then their relationship is represented as a causal link, direct link. Given the parents in a graph, each variable would be independent of its non-parents and non-descendants. This is the Markov condition theory behind this. And the joint distribution of many variables could be summarized like this: the product of these given their parents, basically, and some parameters to be estimated. Basically, that's the central idea. In practice, you need to understand at least some idea about what the graph looks like. Basically, what variables are causing what variables. But in many applications, you don't know. And we'll provide an example right away. You have some idea, but you don't have a full picture. So how do we estimate a directed acyclic graph based on data? Now, this is sort of a magic thing from AI. Let me just illustrate with an example first. So in this study, we wanted to understand whether health is related to finance. This is based on the survey data. And we classify the survey data's questions into 4 dimensions: health, finance, life, and work. So basically, there are 4 groups of survey questions. And then we have 4, they are summarized into 4 variables. We wanted to specifically understand whether health is driving finance or finance is driving health. And this is a debatable question. A few years ago, we found that health is driving finance. More recently, we found that finance is driving health. But in reality, we know that they are probably bidirectional. But this methodology is only one way, cannot handle bidirectional relationship explicitly. So one way to do it is through bootstrapping. You can bootstrap it, the data many times, and then see how many times one is driving another. So in this case, more than 50% of the times, finance is driving health. So since we don't know which one is driving which one, but we do know that certain demographics would not change certain things, or would not change each other. And so we basically have a prior or expert opinions on what might be driving what, but we don't know which one is driving what. So we put it in the data. This sort of algorithm would automatically come up with a diagram like this. This is how powerful it is. And then we know some idea, okay, health and finance are driving life, and so on. And health and finance are driving each other. So it's just an interesting thing. So just wanted to list all the steps under the Pearl approach. First, we construct a DAG. Basically, we have some idea what may be driving what. We know that gender cannot change age, for example, right? So we know that certain things would not happen, but age would just increment by 1 year every year. So, but sometimes we know something would not happen, or something would happen. Sometimes we don't know a lot of things. So, but we construct a DAG based on our domain knowledge as much as possible, and then we collect the data. We plug the data into these one of the structural learning algorithms, also known as causal discovery algorithms, to have a complete graph. And then we identify which ones are the confounders to control for. And then we estimate the treatment effect. Estimating the treatment effect is basically more or less the same as the Rubin causal approach. right? But in addition, this approach adds the structured learning and so on. So it provides a more complete picture. I won't spend too much time on the algorithms, but basically there are multiple algorithms, a lot of algorithms now, and it started with something called PC, which is mostly based on conditional independency test, basically based on statistical tests first. And then the second approach is based on a BIC score. And the BIC score looks like this, basically it's basically the likelihood function, log likelihood function minus something. And you want to maximize that. Or the combination of the above. And tools like BN Learn and others have a lot more algorithms. So in addition to what I just went through, this is another practical example, at least in the business world. Let's say you are changing a product or doing some kind of
Can
Go
I
ahead.
break in for a second to
Yes,
ask
please.
you a few questions that have accumulated?
Go ahead.
Okay, so the first question is actually going back to the Rubin causal model. One of our participants would like you to explain the difference between propensity score matching and synthetic control.
Okay, so I will talk about synthetic control in a moment. So if you can, if they can wait, yep.
Another participant is asking kind of a philosophical question about how often does, based on empirical experience, does correlation not equal causation? That's a tough one, but I'll let you give a few thoughts on that. Is there an estimate based on empirical data around the % of cases in which correlation does not equal causation?
That would be a great question. I want to find out too. So how often correlation does equal to correlation causation, and how often it does not? I don't know the frequency. It probably depends on the context, you know, your field, your business, and so on. But in my personal experience, yes, they are quite different in many cases, if not all cases. Okay. Because of the confounders. It depends on how many confounders are there, how much the confounding effects are. If the confounding effects are very minimal, then they're very close. Hopefully that answers the question.
Yes, and one more question. So how can the Pearl causal model be applied if domain expertise is not available?
Right, that's a great question. So if the domain expertise is completely, in most cases, it is available in some way, but we just don't have a complete picture. But even if you don't have any idea which one is causing which one, just plug the data into the structured learning algorithms. It will at least provide you a recommendation what the causal model, what the causal structure might look like. Now, there's no guarantee that it will be accurate, but it gives you some recommendation. And then you can apply your expert's idea. Hey, this doesn't make any sense. Let's try another algorithm or change the hyperparameters and so on.
Okay, that's great. Thank you, Dr. Lowe. You were following up with her follow-up question, which was, would you recommend applying those methods, the structured learning or Bootstrap, to construct the DAG?
I've been having fun with it, so of course.
One more. In the study of health and financial impacts on well-being, couldn't there be a confounder driving both health and financial factors instead of their arrows going both ways?
Yes, we actually control for the confounder. We just need to show it here. The confounders are things like basic demographics, age, gender, and so on. They are actually driving all of those. So we control for those in our analysis.
Thank you.
Great question. Thank you. Thank you. So in the business world, we wanted to understand some kind of interventions. Interventions could be advertising or marketing things like email outbound, or you just change the look of an ad, color, whatever, or change the price. We of course wanted to understand the impact of these things on some real business outcomes, such as sales, customer retention, and so on. But quite often there's an intermediate step, which we could call them engagements. Do they click on the page? Do they actually use the app? Do they attend a webinar like this? Do they actually go to a store? So those are the engagement. The engagements may not imply revenue or cost, but they could drive cost. They could drive outcomes. So here's just a practical diagram showing that it would be great to know what is the direct impact and what is the indirect impact through engagement. Sometimes when you do an intervention, there's a direct impact on sales. Sometimes you have to go through all these things to get to that level. So if we understand, if we can separate the direct from indirect impact, you can optimize intervention, or you can fix certain things in the right way in order to maximize your ultimate outcome. So that's how powerful it is. And so part of what Pearl did is to separate the direct from the indirect impact, and which is extremely useful, and also extremely useful in the medical world.
Dr. Lowe, this is a good place to chime in with this question from the participant, one participant. In all this discussion of DAGs and different models, could you comment on the relationship with structural equation modeling?
Yes, they are extremely highly related. In fact, DAG I think relies on the structural equation model in some way. But in structural equation models, we often have to have a better idea, a good idea, what variable is driving which variable. And we put it in a graph first, and then we use statistical tests to see whether those things should be there or not. In Pearl's approach, especially under structural learning, it's possible that we have very little idea or no idea what the graph looks like. And the algorithms, which are based on statistics and math, would automatically come up with at least a recommended graph, whether or not you have some idea what is causing what. So that's the key difference, I would say. But they're highly, highly interrelated.
Thank you. We've got a couple right now, so while I've got you interrupted, I'll go ahead and ask them.
Go ahead.
Are there causal discovery approaches that handle hidden confounding? After all, it's unlikely we can capture all possible confounders or colliders.
That is an excellent question, actually. Is this approach able to uncover hidden confounders? No. So we have to have some idea which one may be causing which one. At least if we don't, at least we can capture those variables and plug it into this software for causal learning, and it will give you some idea. But if you don't have those variables at all and you have no idea, no, this does not. But what I'm going to talk about next may help from the economics world, from the third school of thought.
Okay, two more already in the chat.
Okay.
Could you please provide a concrete example of a confounder?
So as I mentioned that in one of the previous slides that if you look at historical data or historical sales data, you capture the data, which customer was contacted by which sales rep. Okay, and then you also capture the outcome, whether they bought something or not. But because the sales reps cherry picked using, let's say, income or geography. So the income and geography could be a major confounder, because if they cherry pick those who have higher income or living in certain wealthier geographic areas. But those things also drive whether they would buy a product or not. So that's a common confounder that we see a lot in the business world. Hopefully that answers the question.
Thank you. Which packages would you recommend for causal discovery in Python? I've been using Causal. Still, I have found many limitations when dealing with, for example, categorical variables using binary variables. My experience with these algorithms is that domain knowledge is indispensable.
I am not familiar with Causal, but I would recommend Do-Y. Do-Y is very comprehensive. Hopefully that answers the question.
Okay. And one more. I think this will be another slide to go back to. In your finance drives health drives finance example.
Okay.
If finance drives health approximately 50% of the time. I think that's going to be like a math counts question here. You better write down these numbers. And health drives finance approximately 50% of the time, which was the case in your estimated DAG. Can't it be interpreted to mean that neither really drives the other?
So this is where we need the domain expertise from. Uh, we actually worked with psychologists, and we also read a lot of psychology articles. And in many psychology articles, to my knowledge, they could be bidirectional. Okay, health may be slightly more important, but this could be a bidirectional relationship. So we almost have to validate it with some other studies. So that's one way to do it. Hopefully that answers the question.
Thank you. You're all caught up?
Okay, thank you. All right, so in the interest of time, I'm going to go faster because Victor Chen still has to talk about the next. Okay, so school number 3 is from economics, which has a pretty long list of methods. I won't have time to go through each of them, but I will talk about some of these at a high level. And again, it's represented by many, many books by great econometricians and economists. Okay, so one of the perhaps the most basic one is called DID, difference in difference. So how do we do that? This is, I would consider, the most basic causal inference method. Let's say you want to measure the policy change. It could be an economic policy or a health policy, healthcare policy, and you have 2 states, right? One state had to change, and the other state did not have that policy change. You want to measure before the time when the policy was changed, what the outcome was in each of these 2 states, and then you do the same thing post treatment. Okay, then you basically take the difference between post and pre for one state and post and pre for another state, and then take another difference between them. Just a very simple subtraction. And then this in this case, the solid line is the control state, and the dotted line is the treatment stage. In the treatment stage, because it was treated, the line is higher. And if you project from the solid line to the dotted line, it becomes another dotted line, but in reality it's higher because of the treatment. Then you want to measure the treatment effect. So this is an extremely simple thing. It has a strong assumption, which is the parallel trend, which assumes that treatment and control states or treatment and control groups have a parallel relationship over time. This is perhaps the simplest method, as I said, and you could use it for model monitoring, because people build AI models or predictive models to do all kinds of things, and you may or may not be able to do A/B tests. A/B tests will be the best among the best, and if without that, what can you do? Well, you can measure the treatment, the model effect, the treatment effect of the model using the model in this way. This is very, very simple. Okay, and economists came up with that. So someone mentioned about synthetic control method. Victor Chen can probably talk you more if he talk to you more about that if he has the time. So essentially, it's different from PSM. Instead of weighting or matching, you will find many groups or many states to match to the treated state. Let's say the treated state is Massachusetts, and you are not sure if Rhode Island is a good match to Massachusetts. But you can try all the other states, all the other 49 states combined. But then you want to find a way to mimic the states of Massachusetts before treatment using a weighted combination of the 49 states. And once you do that, you can apply the same set of weights to post-treatment. And then you can measure the effect. So instead of using one state as a control, you can use many states as a control, as long as you can assign appropriate weights to the 49 states. Another way to do it, this combination. So economics and the statistics approaches have no contradiction to each other in a way. You can combine them. So in one of the papers that I was involved in, which is about measuring a health policy, so we actually combined difference in difference and propensity score matching, just because the DID has some assumptions, PSM has other assumptions, and you combine them. All right, so I'm going to go fast on this one. This is another practical case that we see from time to time in the business world. You have a call out program. Basically, you have a call out program to see whether and you want to see whether the program works. Okay, so you call customers and you hold out some customers not to call them. Let's say this is an RCT. Okay, then in an RCT we can measure uh, the effectiveness of this call out program. And this is called intent to treat, because the call out program is only effective if someone actually answers the phone, right? And in many cases, I'm sure many of you, including myself, receive spam calls all the time, and I receive multiple calls like that every day, day and night. So so that's why I don't pick up calls from strangers. And many of you are probably doing the same thing. But the phone call, at least theoretically, would only be meaningful if someone picks up the phone. So those are called compilers in an economic sense. So the business folks want to understand the causal impact at this level. What's the effect of the phone conversation? Basically, the treatment effect among the compilers, people who actually pick up the phone. Now, how do we do that? There are multiple ways to do that. Those who are familiar with propensity score matching could try to figure out a way to mimic C equals 1. C equals 0 is not the same as C equals 1 because this is not random. This level is not randomized. People who pick up the phone would be very different from people who don't pick up the phone, right? You'll think that way. So you have to find a way to mimic the C equals 1 folks from the folks who are under C equals 0. But it's hard because you don't know. There may be confounders, there may be unobserved confounders. One of the audience asked, we don't know what the confounders are, and there could be unobserved, unknown confounders. What do we do? All right, so now we can borrow from economists. We can use instrumental variable. And what is instrumental variable, or IV? Now, IV means IV only affects the outcome through something else, through the actual treatment. And IV does not impact the outcome in any other pathway, and that's called exclusion restriction in IV theory. So in this case, attempt to call is a perfect, or Z is a perfect IV because it's especially it's randomized at this level. But the actual treatment is actually whether they pick up the phone or not, the phone conversation. Okay. So in the interest of time, I'm going to just quickly go over it. Basically, the average treatment effect of the intent to treat, you can decompose it like this. Parts for those who pick up the phone versus who didn't pick up the phone, there are two parts. But for those that didn't pick up the phone, most people can assume that there's no effect. If they didn't even pick up the phone, what's the effect of the phone call? No effect. And then without that part, it becomes easy. Then the ATE of the compiler, which is what we want to figure out, is just one divided by the other. And this estimator is known as late local average treatment effect. It's related to some Nobel Prize winning methods, of course. Okay, so why do we care? Because number one, this provides a direct attribution to the real treatment, if you will, the phone call. Second, if the attempt to call program, the impact is low, is it because there are very few people who pick up the phone, or the phone conversation is not effective? And then if you know which one is the weakest link, then you can improve that one. So this has a powerful thing. So I won't have time to get into uplift much, but I just wanted to briefly mention that what I've been talking about is measuring the overall average treatment effect of a group or of the population. But quite often, we want to understand the individual treatment effect or conditional average treatment effect. Basically, average treatment effect conditional on certain demographics. If we know who are most likely to respond to whatever, it could be a medical treatment, we can optimize the outcome by giving them the best treatment at the individual level. So I proposed this 20-something years ago. And at one point, people didn't listen to that because they didn't find it useful. And in marketing, most people at the time were just building models to find who are likely to buy what. But if they're likely to buy something, they might be doing it anyway, with or without your marketing intervention. We wanted to measure the marketing intervention, the effect of this marketing intervention at the individual level, and then we can optimize it that way. So until about 10 years or so, when Obama was doing his re-election campaign against Mitt Romney, and the Obama campaign actually used uplift models to find people who are most persuadable, switchable from one to another, from Romney to Obama. It became highly successful, as we all know. And then since then, to my understanding, it's been highly used in every presidential campaign in the US, as well as many local political campaigns using uplift models. And one basic example is actually not from the business world, from the medical world. Then you want to find out what drug would be most effective, beneficial, because if someone just has a cold, has a mild cold, you give them some medicine, it may be a waste, and sometimes could be even harmful. So we want to find out, if you give the medicine to someone, what would be most beneficial. So this is just a list of software that I won't get into for uplift, and this is just a graphic to show that causal AI versus prediction. One is predicting an outcome, the other one is predicting the impact of an intervention. So they are quite different. They're very different things. Of course, causal AI utilizes predictive modeling in many cases. So why do we use causal AI again? So because it tells you attribution, explanation, optimization. There are many schools of thought. Uplift model takes it to the next level, from group level treatment effect to individual or conditional treatment effect. So it's more powerful in that way. And there are plenty of applications. So I'm going to stop sharing. Go ahead,
Thank you,
Nancy.
Dr. Lowe. Yes, there's no more questions, but I just wanted to share that there's been a robust discussion in the chat back on the question of if there are algorithms that can find hidden confounders. And the algorithm has brought up PC and FCI. FCI was particularly identified as being able to find that there is the existence of a hidden confounder. And then there's some discussion about the size of the DAG that these algorithms can deal with. So there's not a direct question for you, but I wanted to tell you that you were spurring that discussion, and see if you wanted to offer any comments in that area before we pass the presentation to Dr. Chen.
I don't have any further comment. As I mentioned, instrumental variable is one way to deal with the hidden confounder issue. Thank you.
Okay, thank you, Dr. Chen. We'll turn the presentation over to you.
Thank you. Let me share my screen. Thank you, Nancy. Thank you, Dr. Lowe. First, thumbs up if you can see my right screen.
Yes.
Okay. Yeah, so I enjoyed Victor Lowe's presentation, which gave us a good depth of the current state of causal inference, including experimentation and then causal inference using observational data. And my presentation hopefully can lead us to think more forward and connect better between causal reasoning and AI space in the current world. Now, before I start, I want to give everybody a pre-warning that don't expect me to be the technical expert on all the technologies I'm going to go over. I present more from my experience as an observer or user in the business of many of the technologies. Now, first of all, to tee up the topic, I see what's the relationship among the three concepts: AI, machine learning, and causal reasoning. So I see AI is an overarching concept whose goal is to create computer systems designed to execute the tasks that are generally linked to human cognitive functions. In that sense, machine learning is one branch of AI. It concentrates on building computer systems that can learn and enhance the model performance based on experience without the need or direct programming. And eventually, causal reasoning, which is a human cognitive function, which distinguishes humans from other primates, is eventually going to be part of AI. If AI can really imitate all the functions human cognition can do. And causal reasoning is a function that is applying logic and evidence to derive conclusions about cause and effect dynamics relationships, often considering counterfactual scenarios. And people can do this in logic or by drawing empirical evidence. But right now, I don't think AI can fully capture that human cognitive function. Eventually, we may get there. Right now, a lot of the attempts of causal reasoning using AI requires a lot of assistance from human experts. But throughout the last few years, especially the last 6 months, we have witnessed a lot of major progresses made in the industry in this effort by GPT, O1 Preview, Google Gemini, Cloud Nova Pro by Amazon, and then there's a new competitor from China called DeepSeek. Everyone is competing in this space of reasoning, including causal logical reasoning. So this is how I see eventually all the three concepts. So AI is overarching concept, ML is one subset, causal reasoning is another subset. And I see the two subsets often overlap. And then today I'm going to focus on the overlapping part of the two subsets between machine learning and causal reasoning. So I will hopefully give everyone a good breadth of the current advances in this overlapping area, including reinforcement learning for experimentation, causal inference, causal discovery, causal machine learning, causal large language model, and then eventually agentic AI, joining all the capabilities of AI together into one flow. So let me go through them one by one. Let me start with the reinforcement learning. So at a conceptual level, reinforcement learning, or RL, is a branch of machine learning that focuses on training agents, which is a computer system, to make decisions in the environment for the purpose of maximizing cumulative rewards over time. So it operates on the principle of learning through trial and error, where the agent, the computer system, interacts with the environment. And the environment could be the market, the customers, the investment, stock market, the voters, etc. And then learns how different actions may trigger different rewards or penalties as feedback, and then adjust the interactions in order to maximize the rewards and minimize the penalty. And over time, it will optimize the options in order to maximize the accumulated rewards. Now, in the business area, in the business community, the most popular application of reinforcement learning for causal analysis is arguably multi-armed bandits, or bandits in short, as many people would call it. So it is a technique to balance exploration and exploitation. What does that mean? So exploration is, okay, I just try different experiences, variants of treatments, experiences to customers, or portfolio allocations for investments, or different messages to voters, and just to learn how people react from the environment. And then based on sufficient number of learnings, I adjust. So I would recall some of the variants and then increase the exposure of some other better performing variants, and then learn again, and then come back to adjust, then learn again, come back to adjust. So it's an exploration plus exploitation in iterations in order to adjust the combinations of the treatment experiences in order to maximize the cumulative rewards over time. So let me use the I think everybody has some exposure to social media, YouTube or Google News, Instagram, etc., or Netflix. So you may wonder how the configurations of the interface were decided to us. So initially, there would be a lot of different ideas of configurations of different user experiences or configurations. Let's say there are 3 different configurations, variation A, B, C, but we just don't know which one works the best, can best convert the traffic into customers, or into signed up accounts and paid accounts, etc. So in the traditional A/B testing, randomized control trial, which Victor Lowe explained, let's randomly split the traffic or the potential customers into three groups. Then for each group, we assign a different configuration of the experience, and then wait for a few weeks or a few months until we have enough sample size, and we can compare the outcomes and see what's the conversion rate across in each of those 3 different groups, and then we pick the winner, and then roll out the winner to everybody. So that's the traditional A/B testing. Randomize, split out, wait up for a long time, find a winner, roll out. Now, but the downside is we are hurting 2/3 of the traffic, right? So only if only one is winner, then the other 2 are losers, and then those people in the traffic in the 2 less performing variants are getting hurt. So we might lose those people. So model bandits is more dynamic. So same concept, 3 variants, but we learn something from the conversion from the traffic, and we come back to make adjustments. So the better performing, more converting versions would gradually receive more and more traffic in the allocation, and the worst performing ones will gradually receive less and less traffic until it dies out. It receives no traffic. So if you plot the traffic exposed to different variants over time, this is how multi-end bandits testing will look differently from traditional A/B test, right? So, and then overall, you could see we expose more people into the winning version. In this case, it's version C. So we're not hurting a large portion of our potential customers. Now, one special case of multi-armed bandits is called contextual bandits. Now, it goes further. So the purpose is not to pick one winner that fits all by dynamically adjusting the exposure, exploitation over time. But the argument is, okay, people are different. The voters are different. Customers are different. Investors' preferences are different. So it's not about finding one size that can fit all, but let's find the best fit. So we learn not only the responses from our customers, from the voters, from the environments, but also we learn the audience characteristics, right? Demographics, income level, educational level, the life habits, lifestyles, etc. And then we try to find out how those characteristics may decide or moderate, in many cases, the responses. So it's not which version among the 3 would win all the traffic, but how should we optimize the allocation of different variations to different people based on audience characteristics? And then it's still reinforced learning because it's making adjustments over time to find the best fit. But then the objective function is no longer finding one winner. The objective function is to maximize the fit over time, because there's no universal winner or loser. There's only the right variant for each individual performance of individual subject in the test. So the overall goal of contextual bandits compared to multi-arm bandits or A/B testing is to personalize rather than picking the single best option. Now, this is almost everywhere in the business applications where the goal is personalization or optimization. So we would see UI, UX personalization, which I mentioned. We would see dynamic pricing. So whenever you open your Uber, Lyft app, you see the price is changing depending on your location and the local conditions. So it's dynamically adjusted to maximize the price given the traffic, supply and demand. There's also content recommendation, YouTube, social media. So everything is personalized after they have learned enough what you like in the past and all the information you provide about yourself into your account. There's also sequential portfolio selection for investments. So learn how the markets will react to different application, and then making adjustments over time rather than set the portfolio as fixed going forward. It's dynamically adjusted. But the limitations of reinforcement learning, especially bandits, are also obvious, which explain why many businesses, knowing the benefits and the flexibility of bandits, it's not applied everywhere. So we still see traditional A/B testing, ABC testing in many cases. That's because a lot of times the responses from the testing subjects, the voters or the customers are not that frequent. So you roll out something, it takes a long time for them to react to it, right? So for investment accounts, for example, people don't log into the account every day, and voters don't talk to the campaign teams every day. It's not very frequent. So it will take a long time to learn enough information and make adjustment. So eventually it's like the A/B test, just roll out something, wait for a long time, collect the data, then make adjustment. So that's one. The responses are not frequent. We don't learn enough. We don't have the time. We can't afford a long time horizon to collect enough responses to make adjustments. And also the sample size might be too small. There are not many people in the pool of testing. And if we split the test into 3 equal groups, we may already struggle in getting enough sample size, enough power sample size to still significant over time. If we have to reduce some groups to even smaller sample, which is the underlying mechanism behind the bandits, then we will be struggling even more to get a sample size. And sometimes we just can't adjust quickly, right? I mentioned the sequential portfolio investments, but for a lot of the markets, if you want to sell, there's a cost of trading. So you end up losing a lot of money by making too many adjustments over time. So let's close out the first example of overlapping between AI and causal reasoning, which is quite widely applied, but it also has limitations that constrain the scalability of this application to everywhere.
Let me jump in with 2 questions that have accumulated for you.
Okay.
One is about validation. So once a causal model is built, how can it be validated?
Once a causal, for A/B testing, we don't need any causal model because there's no confounder, right? So everything's randomized. It's the only reason for somebody within one experience, one variant is random. But I think the question would apply more to causal inference of observational data. And hopefully I suggest we hold that, and then maybe I can come back to the question when I start talking about causal inference of observational data.
Okay. Could a variation of Thompson sampling handle the situation of small traffic over time in multi-armed bandits?
Well, Thompson sampling is actually part of the one of the techniques used to randomize traffic over time. Again, I don't have the depth of the technique, but I'm aware as a user of multi-armed bandits, Thompson sampling is used as one mechanism of randomizing the traffic, but there could be many others.
Okay, thank you.
Right, let me move on to the next. The next is causal discovery. I can go this very quickly because Victor Lowe had already touched this topic quite extensively. So causal discovery is we only have data and there's no domain knowledge behind. But how do we know what we have a bunch of variables and the data labeled by different variables? We just don't know what variable causes what others. And we don't have any domain knowledge to make judgment to build or assume a causal structure, model, or graph beforehand. So causal discovery could be used in that case. Just let data drive the discovery of the causal directions among different variables. So one analogy people often use is, okay, the causal discovery from data without knowing any domain knowledge of causality is like predicting the shape of an ice cube based on the puddle it left on the kitchen counter. Right? It explains very accurately what that is about. One is it's not accurate because there's no domain knowledge to judge to verify the correctness of the model coming from data. Second, it's quick, right? It's automatic. Just let the shape of the data tell the story. Let me skip this. I mentioned two things. So compared to causal inference, which would require that there's some domain knowledge in advance to assume or build or hypothesize a structure of model graph connecting the causal directions among different variables. In this case, the input is just a bunch of raw observed data, no prior knowledge of the causal structure. And output is also different from between causal discovery and causal inference. So what people want to use causal discovery is try to draw or represent the directions between of causal relationships between different variables. But causal inference, we already have this structure. So the purpose is to quantify the estimate of the causal effect size, such as average treatment effects or local average treatment effects, etc. So the purpose is different. Let me skip how this is done. Let me skip some of the technical details, but happy to share the slides after this event. Now, there are, I'm aware of some applications, not a lot, because for important decisions, we can't just let raw data tell the story. What if the variables don't contain all the key variables that are necessary to construct a causal model? But I am aware of some applications. And actually, when in my old job at Fidelity, I often attend some of the pitches or demos by different vendors. So I've seen some attempts to apply causal discovery as the first sort of preliminary hypothesis of the relationships among some key variables. I've seen use cases in customer retention. So there are a lot of customer data from customer relationship management software, and how to connect different columns of data into a graph, and also what variables are causing the cost reduction in budget allocation. I've seen some of those use cases, but in almost all those use cases, the graph requires some level of human domain, human expert validation. So nobody would use the graph automatically from the data directly into an analysis or judgment or decisions. It requires some human validation in the end. Yeah, so limitations, key variables. If the variables are not in the data, we cannot capture it. And this could also be overfitting. So it's automatic. It's just trying to, like machine learning is trying to fit the story into the data rather than generalize a story out of the data. And then there's a challenge called equivalence classes, because there might be multiple causal graph models that could fit into the data. And then if there's no human subject matter expertise to intervene, it's really hard to tell which one is the right one. It's both can fit into the data perfectly. When data sets are large, when there are too many columns, the computational complexity is high. It may take a long time to finish the job. Now, the next topic I want to cover is causal. Yes, let me pause, Nancy.
Okay, thank you. Do you have a sense of how much data or how big an N needs to be to do causal discovery based on how many variables you're looking at?
I don't have a definite answer, but it should not be too many. So causal discovery works well in moderately sized data, not in large data, because it takes a long time to converge and then get to the story. But it can be too small. Otherwise, there will be, if the sample size is too small, there might be too many different equivalent causes models that can fit a story. But it can be too large because there's a computational cost to it.
Thank you.
Not the best answer, but I think the key is it works on moderately sized data at the best.
Do you have some examples of what moderately sized would be?
I don't.
Thank you.
Now let me move on to the next. This could be a topic on its own, causal machine learning, which is using machine learning to analyze observational data to estimate the causal effects. But for the sake of time, I'm going to focus on probably the most adopted approach, which is double machine learning. It's one branch of causal machine learning, but it can a lot of other machine learning efforts, techniques have been used to draw causal inference, such as causal trees, causal forest. But today, let me focus on double machine learning. So it seems to be a pretty new thing, but when I look back into the seminal paper, which is this one, Double Debiased Machine Learning for Treatment and Structural Parameters, published by another Victor Chino-Zhukov from MIT, and then his colleagues. It's been a long time, and the first conference paper was published in 2015, so it's been about 10 years already. So time flies. Now, in essence, this is what double machine learning is trying to do. Now, the assumption is, if you focus on this graph, so Z is the confounder, D is the treatment, and Y is the outcome. So what it's trying to do is, so we know both the treatment and outcome are caused by the same factors, and we can observe those factors, or in Z. Then let's remove the variation in D that is caused by Z, and remove the variation of outcome that's caused by Z. And then let's analyze the relationship between the two residuals and see if there's any relationship left, and use that relationship to infer the causal impact of D on Y. So it works in 3 steps. 1, predict D based on Z. Get predicted value, get a residual. Predict Y based on Z using machine learning. Get a residual, removing the predictable part. Now run a linear regression of the residuals from 2 on the residuals from 1 as the linear estimate of the causal impact. Now, there are many other variations of double machine learning, but this is probably the simplest one, which is called partial linear modeling of double machine learning, assuming at least between D and Y, this is a partial linear model. Now, it's being applied to many things, especially when the data is longitudinal, right? So we know the confounders, but we cannot observe changes over time. We cannot do matching. We cannot do synthetic control, and compare the changing patterns, the trends over time, which Dr. Lowe presented in some of his slides. But let's remove the known biases from the data first. Let's debias the data. One example I've seen, and it's from a published source from Netflix, is now how do we know the content we push onto a user's billboard is causally driving the users to play, to click to play, to purchase, right? The content. Now, one example is Squid Game. Squid Game is very popular, a lot of subscriptions, and then should we attribute our success to our decision to put Squid Game onto the billboard, or people just play billboard anyway because the audience love Korean content, and then there are a lot of Korean content on the billboard, and then they also because they love Korean content, they also play Squid Game because it's in Korean. Now, we could measure how much people like Korean content by observing their behaviors of watching other Korean movies, Korean shows, etc., and then use double machine learning to remove the predictable portion of the treatment, which is put Squid Game on billboard, and then the action of play Squid Game out of the data, and see if there's anything left. And then if there's a significant impact between the two residuals, then we can infer there is a treatment effect. That's one example. Another example is also from public source. How do we know that our long-term there's a long-term return on investments? If you look at this assumed causal graph model, yes, current investments are what we did, and we observe long-term some index that could lead to projected long-term revenue. But how do we know there's a direct causality other than, okay, because there's a past investments, we target the right company demographics, the revenue in the past is high, and other proxies, and they drove us to make more investments today. At the same time, they accumulate and led to long-term revenue in the future. So there's no direct causality between our investment today and the future revenue. It's just they were just caused by the same thing. Now again, if we could measure and observe and measure all those potential confounders, we could debias the data from our measures of current investments and long-term revenue using double machine learning and see what is left in this relationship to infer causality. It's not a perfect method, and people coming from quasi-experiment school are highly skeptical of this methodology because it's making very strong assumptions. One of which is, okay, we can observe all the confounding. We don't need to worry about other variables that are not in the model, which is almost always incorrect. And then there's a root and consistency. If the sample size is large enough, the measure is converging to the true measure. And the model selection. So especially for partial linear regression, it's controlling for covariance to remove the covariant influence from the outcome. But there could be bad control examples, which I'll give you one momentarily. And also, machine learning is not very interpretable, right? So we ask machines to remove the predictable portion of the treatment and the outcomes, but how those confounders affect the treatment and outcome are relatively unknown. It's a black box. And then related to the first limitation, DML, double machine learning, cannot account for unmeasured confounders. If we cannot observe, we cannot measure those hidden confounders. Now, give you one example. This is from the work I did in the past. So assuming this is the right causal graph model to represent all the relationships among different personal demographics, family status, household income, financial income, and how they play a confounding role in both our propensity to sign up for 401k, that decide our eligibility of 401k, and how they affect our net financial outcome in our account. Now, double machine learning can, if this is a correct model, double machine learning can debias the data, and then for us to estimate what is the true causality between the 401k eligibility and our financial well-being, right? So to see, okay, 401k is really making people financially better off. But what if we do not observe, and thus we cannot measure some of the key confounders, like the true income, what other financial protection programs families have signed up? And we use a partial part of the only incomplete list of the confounders in the model, machine learning. Then the results would be drastically different. Now, for the true model, we would estimate per person impact of 401k would be almost $9,000 on the financial net wealth. But if we missed a certain key variables, we would mistakenly attribute 401k to more than $14,000 on the net income. It's a huge difference, huge margin, error of margin. So let me close out the causal machine learning.
Can I interrupt with a question about double machine learning?
Yeah, sure.
Okay. Does double machine learning provide uncertainty interval estimates for average treatment effects and conditional average treatment effects out of the box? Or is this a function of the underlying machine learning models?
It does. It does. So if I don't think I fully understand the question. If the question is asking, does it provide some sort of reliability confidence interval? It does. Like this example here. Just like any other average treatment effect estimation, it provides the point effect and also the reliability, the confidence interval.
Thank you.
Now let me, I know we are wrapping up very quickly. Let me quickly go through the last two topics, causal AOM. So it's a very emerging area, especially since last year. People start poking LLM models to see how they can talk causality, how they can represent causality, how they can extract causal information from large texts, and how they can infer counterfactuals from qualitative and quantitative data. One of the first efforts I've read is a Microsoft publication in 2024. They examined how GPT 3.5 and 4 at the time inserted causal texts just by feeding different causal questions in the text. And then they figured out those models can discover causal relationships at 97% accuracy. They can make a counterfactual reasoning, like answer question, what would happen if something did not happen? What's the outcome? They could answer those questions, 92% accurate. They could tease out necessary and sufficient causality between different events at 86% accuracy. So it's pretty impressive. I'm gonna skip this because I also did some similar tests just by directly interacting with the Copilot and cloud interface and see if they can do the same thing. Maybe they can just skip to the end. So I feed some text and ask, okay, extract all the causal relationships from the text and build a causal graph. It's trying, but clearly there's a lot of mistakes, and they can only capture the face value causality. So people talk about causality, I would call those causal parrots rather than causal reasoner, right? There's no reasoning. They just read the text, and then if something appears to be cause and effect, it takes them out, extract, and then represent into a causal model, causal graph. Let's skip this, and then more and more people are testing different LLM models on those tasks. Counterfactual reasoning is getting better, but still not very accurate. Necessary is sufficient. It's getting better. One thing I found is if you feed reliable training text as prompt to train the LLM models, the accuracy increases remarkably. So it's going to be a human-machine interaction. Now, let me close out. What does all this lead us? So we have all the machine learning techniques being used or tried to accelerate or improve the performance different causal tasks. What can this lead to us? So think about how humans embrace reasoning and domain knowledge in order to make decisions. So they use the prior knowledge in the past. They build a causal model, and they start experimentation or causal study design, collect data, processing data, model, run analysis, write down the findings, maybe checks and balances for peer reviews, then present a report for making decisions. So that's how humans do this. Now, interestingly, we have seen some efforts, not in the business, not in the practical world, but in academia, trying to imitate, using AI to automate and imitate the whole process from end to end. Just a few days ago, I think, there's a new publication from a team between Johns Hopkins and then for the other company. So they tried to imitate human performance by fully automating with some human feedback to represent the whole loop. And then there were some very interesting findings. In summary, the machine learning coding has achieved very high performance, just like a human machine learning engineer. If human can provide feedback at each stage, before the next stage, the performance, the quality could significantly be improved. And also compared to the previous automation techniques, now the cost for doing this is only 60% of the past, of last year. So the cost is down, performance is higher, and if we can inject human feedback into the stage between different stages of the workflow, the quality is also pretty high. So I think this is what all this AI revolution is leading us to better assist humans as our agent to reason and analyze causalities of the world. So let me close this out here because I see we are a bit running out of time. And if there are more questions, I'm happy to answer them.
Okay, thank you very much, Dr. Chen. It was interesting. I don't have any more questions in the Q&A right now. If there's, I think we're good. I did want to make sure that I said thank you to both of you, and also to note that the speakers are presenting their own opinions and experiences, not their employers. So we really appreciate them doing this on their own time and sharing their insights with us. And since we're over time, we'll wrap up with that. Truly appreciate you. Everybody have a good day.
Thank you. Take care.